Greetings everyone, my name is Umair bin Wahid, and in this talk I'll walk you through our study on automatic picking of stacking velocity using two popular clustering algorithms, the k-means and the DBSCAN algorithm. A bit of motivation in the beginning. So velocity analysis is one of the most important steps in the conventional seismic processing workflow. It provides us with a velocity model that acts as a pivot for post-processing operations such as time-to-depth conversion, seismic migration, and even full waveform inversion, etc. Traditionally, velocity picking is done by manually picking peaks in some coherency measure like semblance. Unfortunately, this is a tedious and time-consuming process. In fact, manual velocity picks are quite subjective and depend on the processor's preferences as well. Therefore, researchers have long been looking into the problem of automatic velocity picking, as it would significantly reduce cycle time. These efforts could be traced back to the works of John Toldy, David Lumley, and others. Essentially, what they did was to transform the velocity picking problem into an optimization problem. Therefore, solving this optimization problem gets rid of having to manually pick these velocities. Now, among these different efforts, there were also attempts to teach an artificial neural network how to pick these velocities. And as today in the 90s as well, neural networks were gaining popularity, and there were a couple of authors also looked at using those primitive neural networks to pick velocity automatically. Now, with the recent advances in capabilities of these learning algorithms and also our computational power, people are now looking into the possibility of using these algorithms for velocity auto picking as well. And this goes back to several of these SCG abstracts recently published, where people are trying to train very advanced neural networks such as convolutional neural networks and recurrent neural networks to solve the problem of velocity auto picking. Now, however, one of the problems with these methods is that they are supervised learning approaches, and therefore you need a lot of data to train on, really, and to build a model that is kind of generalizable to different data sets. However, people have also started to look into unsupervised learning approaches. So this goes back to the work of Kenneth Smith, published at the SCG annual meeting 2017, where he was looking at the k-means clustering algorithm for velocity auto picking, and also similar work was done by Wei et al., shown at the EAG annual meeting. Now, unfortunately, these works were really inspirational, but they looked at the simplest clustering algorithm, the k-means. Therefore, we thought, why don't we kind of take this work forward and look at other clustering algorithms, and if they could help us improve the picking accuracy and efficiency of these algorithms. All right, so in this work, what we do is we compare the performance of k-means and DBSCAN algorithm. Both are very popular clustering algorithms for the problem of solving of, for the problem of picking automatic velocities. All right, so here is our workflow. So what we do is we have our CMP gather as input. So x-axis is your offset, y-axis is your time. What you do is you build a semblance map out of it. And here you have on the x-axis trial velocities, and y-axis is again two-way travel time. And what we do next is we take this semblance and pass it through a thresholding filter. So this thresholding filter asks this question, that whether a particular data point has a value above a certain threshold. So for example, take value of 0.1. So we ask at each point in this 2D domain that whether the value here is larger than 0.1 or not. And if it's larger than 0.1, then we keep that data point while we discard all the other data points that are below 0.1. So it's kind of a filter that looks at it's kind of hard thresholding, looks at a value that whether it's above the threshold or below. If it's above, I keep the data point. If it's below, I just discard those data point. And we call this filtered semblance. And what we do next is we input this filter semblance to clustering algorithms, and those clustering algorithms will help us pick velocities. And we'll see in a minute how those algorithms could do that. One thing I wanted to mention, that this workflow is inspired from the work of Kenneth Smith, published in 2017. All right, so before we go on and look at how clustering algorithms will take this filtered semblance and pick velocities for us, let us try to understand what clustering algorithms do. Therefore, we'll be able to understand the differences between k-means and the DBSCAN algorithm. All right, so clustering allows automatic grouping of data sets. Clustering has been used for many problems in science and engineering. This involves something like detecting outliers in your data, collaborative filtering. So when you open Netflix or YouTube, you get some suggestions from the website, and what they use is some kind of clustering algorithm to find out, based on your previous watches, the things that you watched and the things that you might like to watch in the future. So they kind of find those same videos from the same group of clusters. It's also used in gene sequencing, and it finds applications in many fields of science and engineering. Now let's talk about the k-means clustering algorithm, and let's try to understand how k-means tackles this problem of clustering. Okay, so k-means is the simplest and the most popular clustering algorithm. What it does is it partitions the data into k distinct non-overlapping clusters. Okay, now one of the downside of k-means is that you need to tell the algorithm how many clusters to form in the data. Now this information may not be available to you in the beginning, and it's kind of, you need to have some insight into your data, which is not always the case. And sometimes you might not visualize your data if it is in higher dimensions. All right, so let's see how k-means operate. So imagine you have these data points in a 2D space, and what we do is we try to run k-means algorithm to try to cluster this data set. So if I were to ask you to cluster this data and tell you that there are essentially two clusters in this data set, then you would be able to find this as the first cluster and probably this one as the second cluster. And so this is essentially what we will tell the k-means algorithm, that we have two clusters here. Can you find us the same clustering as a human would? Okay, so the first thing that you would do in a k-means algorithm is to define two cluster centroids, and they can be defined randomly. They could be placed anywhere in the domain. Okay, so imagine we place these two cluster centroids at the red location and the blue location. The next thing to do is to compute the distance of each data point from these cluster centroids. Okay, so you calculate the distance of this point, for example, here, from the blue centroid and the red centroid, and you assign this point to the centroid it's closest to. So it gets assigned to the blue cluster. Okay, likewise, we repeat the operation for a different data point, some point lying here. We calculate the distance to both cluster centroids, and we assign it to the centroid it is closest to. And if we repeat the operation for all data points, what we get is we get our data points separated into blue and red clusters. Okay, we know that this is not the right clustering, so essentially what k-means does is it goes to the next step, and the next step is to move these cluster centroids to the mean location of the points it belongs to, right? So you calculate a mean of all these points and place the blue centroid to that location. Likewise, you calculate the mean of all these red points and relocate the red cluster centroid. And essentially what happens is the blue cluster centroid moves to this location and the red one moves somewhere here. Okay, and now what we do is we repeat this operation. So what we do now is we again compute distances of all these data points with respect to the newly assigned cluster centroid location and reassign the data points. Okay, so when we do that, we kind of change these assignments, and now the blue data points have been changed, and all these data points now are assigned to the blue cluster, while these data points are assigned to the red cluster. And the next step again is to move these cluster centroids, right, to the mean location of the data points they belong to. And now once you repeat this operation, you would see that we don't change any data point assignment. So once that happens, you know that your algorithm has converged, and therefore once nothing changes, you know that your solution has converged. And here is your cluster centroid, the red one here, the blue one here, and this is your final clustering. Okay, what about the DBSCAN algorithm? So the full form is density-based spatial clustering of applications with noise. Now, the hypothesis or the assumption here is that data is drawn from an unknown probability distribution function. And regions with high density of points indicate a cluster, while regions with low density indicate noise. Now, the good thing about DBSCAN is that it can recover more complex cluster shapes when data is organized in nonlinear fashion. DBSCAN is able to detect those clusters And one good thing about DBSCAN is that user does not have to input the number of clusters. So you might not know, initially how many clusters to form in your data, and then DBSCAN would be the way to go. All right. However, DBSCAN requires two other inputs. That's called epsilon and minimum number of points. Okay. And what it does using these two inputs is that it classifies the data points into core points, border points, and noise points. Okay, so let's see how it all works. All right, so imagine we assign minimum number of points to 4, which is usually used depending on your application as well. But what it does is, let's imagine it starts with this point here, okay? So what it will do is it will create a circle around it, around this point of radius epsilon, and it will ask the question, do I have minimum number of points in this circle or not? So imagine, when it creates this circle, what happens is we see something like this here, and it starts counting. You have 1, 2, 3, and 4. Yes, we have 4 points, and therefore we classify this point as the core point, okay? And it moves on to the next point, repeats the operation, asks the same questions, and marks it as core point or not, right? And when we reach to the border of the cluster, what it does, it again asks this question, do I have 4 points lying within this circle? So for example, it draws this here circle here. It does not have 4 points, but what it has is, what it does it is, it sees there is one core point, therefore it assigns it as border point. Therefore, to be assigned a border point, you might not need minimum number of points, but you just need at least one core point. Okay, how about noise point? So when you draw a circle around a noise point, you find no core point within it. So when you don't find a core point within a circle, you assign that point as noise point. Okay, and this is how essentially DBSCAN ignores noise and DBSCAN builds clusters, right? Okay, so here is an animation for the DBSCAN algorithm, and what happens is that it starts by asking the same questions and kind of builds this cluster. And once it finishes this cluster, it moves to the next point, and it builds those clusters and continues to move. And then when it comes to these noise part, it sees that there are not enough number of core points in there, so there's not a core point, and there's not even a single core point there, so there's not a border point, and I should ignore these points. Okay. Okay, so this 2-moon data set, and if we feed this 2-moon data set to the k-means and the DBSCAN algorithm, this is what happens. Okay, on the left is the k-means result. So k-means thinks that this part belongs to the purple cluster, so this will be assigned to the same cluster, although visually we can see that, the grouping should be something like this. This is a single cluster, and this is the other cluster, which DBSCAN is able to detect, whereas k-means is not. All right, so back to our workflow. So we're trying to solve the problem of velocity auto picking using these two clustering algorithms. We have our input CMP gather, we create a semblance map, and we build a filtered semblance map out of it by passing it through a thresholding filter, and now we will feed this filtered semblance to these clustering algorithms. All right, so let's go to our results. What happens? Now, because we don't know how many clusters to form, let's say we start with a k of 5. So we say to this k-means algorithm, give me 5 clusters out of this data. Okay, so here what you see is these in black are marked the cluster centroid or the velocity picks, as we'll see in a while, and each different color is a different cluster. So this is what it does, right? And if we map it back onto the cluster on the semblance map, so these are the velocity picks marked by this white cross. Now, as you can see here, we don't have picks in the shallow part of the semblance map, and therefore perhaps the ideal number of k is more than 5, right? So let's try to increase k. How about 10? So k equal 10. So on the left again we see these cluster centroids and these different clusters marked with different colors. What we start to notice over here is that, notice these two cluster centroids. Now this data is kind of marked with pink crosses, and this one is with green, but some of the green data lives here. So this is kind of a dangerous thing, because the algorithm believes that these data points belong to this cluster and not this cluster. So something is wrong here. However, if we map these picks onto the semblance map, then they come out to be like this. So if I go back and forth, it feels like this pick is kind of perhaps not in the right location. Okay, what happens if I increase k? So maybe I don't have the optimal value of k because I really don't know how many um, clusters to form. Okay, how about k equal 15? Now the problem that I identified in the previous case now gets worse because at the same time value, it gives us two different cluster picks. Remember, the data does not have multiples, and therefore this should not happen, right? But what it does is it artificially creates those clusters because it feels that, you know, I need to create 15 clusters, so somehow I have to break even the clusters that were formed previously, and what it does, it gives us two velocity picks for the same time, which is wrong, right? So we run into this problem. Now let's move to DBSCAN and see what happens. So we start with an epsilon of 0.06, and here are the picks, and we don't have to tell DBSCAN, you know, how many clusters to form, so it forms some, I don't know, 10, 12 clusters, but we don't run into the same problem of, you know, having two different velocity picks at the same travel time value. Okay, how about reducing epsilon? So when we reduce epsilon, we force to form more clusters. Can we kind of force this algorithm to run into the same problem? Let's try epsilon of 0.04. Now what it does is it gives us denser picks, but not the same problem that we ran into with k-means. So if I go back and forth, what you will notice is that what it does is it kind of interpolates between the velocity picks we saw in the previous slide. So epsilon equals 0.4 kind of interpolates. How about epsilon equals 0.02? Can we force that problem? No, we don't. What it does again is that it picks those velocities really finely, and it kind of interpolates between the picks that were made in the previous slide with a higher value of epsilon. Okay. So here is velocity comparison. On the x-axis are the trial velocities, on the y-axis two-way travel time. In red is the true velocity, in blue is the velocity picked using DBSCAN, which you see is very close to the true velocity, and in green is the k-means velocity. As you can see in the shallow part, it struggles to give us the true velocity, whereas at the bottom part, it gives us some estimate of roughly the estimate of the true velocity. Now, we picked, for comparison here, k-means with a k value of 10 and DBSCAN with a value of 0.04, just to kind of pick the middle values of the different values we tried. Okay, how about correcting the NMO-Gather? So here's on the left, NMO-Gather corrected using k-means, and you can see here it's clear that the corrected velocity is incorrect. So you could see these smiles here. Whereas with DBSCAN, it's much more flatter. How about we plot errors in NMO-Corrected Gather? So we compute NMO-Corrected Gather using the true velocity, and then we subtract it from the one that k-means gives us and the one that DBSCAN gives us. On the left, it's clear that there are a lot more errors compared to the one on the right, and therefore DBSCAN gives us more accurate velocity picking. All right, now we move to a real data set. So this is a publicly available data set. This is called, I think, Vibro-size data set from Poland. On the left, what you have is the CMP gather. Again, this is the semblance map, and you can see a lot more noise, even multiples here. And then once we pass it through our threshold and filter, we are left with these data points, and we'll feed these data points to our clustering algorithms. So we try several k-means runs with different values of k, and here is what we get. Now, what you see over here, I think, is perhaps a problem because of the multiples, and therefore what we do next is we develop, on top of our clustering algorithms, we develop something called a guiding filter. So we pass our picked velocities on this panel here, and we pass it through a guiding filter. And what this guiding filter does is it tells us that whether this pick belongs to the primary energy or some sort of noise or coming from a multiple. Therefore, when we map it on the semblance map, we get these white crosses, but not the ones here that perhaps belong to multiples or some other forms of noise. And therefore, this guiding filter helps us to remove noise from our real data picks. Okay, how about DBSCAN? Okay, so these are the picks using DBSCAN with a value epsilon of 0.12. And again, we try a few different epsilons, and it's much easier to find an epsilon that works for you, compared to the case of k-means, where you have to try a lot and really finally optimize the value of k. Now here we try a few different DBSCAN, the value of epsilon for the DBSCAN algorithm, and we end up with a value of epsilon equal 0.12 that works the best. And again, we pass it through a guiding filter that helps us keep these velocity picks and ignore the ones lying over here due to some form of noise or multiples. Now, I think what we propose here is that for your first couple of CMPs, you tune this parameter epsilon, and then it's good for the rest of CMPs. While for k-means, you need to tune that, or to tune the value of k for each CMP, and that's kind of problematic. That's something you don't want to do. Velocity comparison here against manually picked velocity by an expert. So in black is the velocity picked by an interpreter, in blue is the DBSCAN velocity, and in green is the k-means picked velocity. As you could see, DBSCAN gives us better estimate of the manually picked velocity, or is more closer to the manually picked velocity, and it also provides us with a velocity in the shallow part where k-means is not able to pick. Alright, to summarize, we study the problem of velocity auto-picking using two popular clustering algorithms, the k-means and the DBSCAN algorithm, and we observed that the accuracy of picking showed sensitivity to the number of clusters when we use the k-means algorithm, while for DBSCAN, it's not as sensitive to the value of epsilon. You just need to tune it for the first couple of CMPs, and then it's good for the rest of your data, of course, coming from the same data set. So whenever you have a new data set, you need to tune your epsilon for the first couple of CMPs, and then it's good for the rest of your CMPs. All right, and we also found that DBSCAN is significantly less sensitive to noise because it is, in the algorithm there is a provision to ignore noise points. And we also build a guiding function that helps us avoid picking noise energy in the data due to multiples and diffractions. And one thing we haven't elaborated on this guiding function is something we're currently working on. Right now what we use something based on a slope function. So if the slope is too high or too low, then we ignore those data points because we believe that it's kind of driving us away from the primary energy. But this is something we are building on, and we are thinking of using some kind of neural networks that we could train with a few examples. Where is the primary energy? All right, so we recommend using DBSCAN with our guiding function, and therefore with that I would like to thank King Fahd University Petroleum and Minerals and RGAS for their support. If you'd like to talk more about this work, or would you would like to learn more, please feel free to contact me. Thank you for your time.